Zero matrix, null matrix. Hello everyone. Today, we are going to begin our discussion on a fundamental concept in linear algebra. As we explore the study of matrices, we will encounter a very special type of matrix where every single entry, regardless of its position, is zero. This specific matrix is formally known as the zero matrix, although it is also frequently referred to as the null matrix. To give you a better intuition of its purpose, think about basic arithmetic. The zero matrix serves a role in matrix algebra that is very similar to the role that the number zero plays when we perform simple addition or subtraction. In the upcoming slides, we will look at the formal definition of this matrix and explore its unique characteristics. Definition. First, we can state that a matrix O is called a zero matrix if every single element, denoted as a sub ij, within the matrix is equal to zero. To express this more mathematically, a matrix A, composed of elements a sub ij, is defined as a zero matrix if a sub ij equals zero for all possible values of I and j. Now that we have introduced the general concept of the zero matrix, let us move on to its formal definition. In simpler terms, this means that regardless of which row or column you examine, every single entry must be zero without exception. Once we have this definition clear, we can proceed to look at the specific notation and characteristics of these matrices in the next slide. Key characteristics. Now that we have established the definition of a zero matrix, let us look at how it is represented and the rules regarding its dimensions. First, regarding notation, the zero matrix is typically denoted by the capital letter O. Moving on to the order of the matrix, it is important to note a key difference here compared to other special matrices. Unlike identity or diagonal matrices, which must always be square, a zero matrix does not have to be square. It can be of any order, which we describe as m by n, where m represents the rows and n represents the columns. Because a zero matrix can take any dimension, there are infinitely many different zero matrices. Consequently, the specific order of the symbol O is usually determined by the context of the operation you are performing. For example, if you are adding a 2 by 3 matrix to a zero matrix, the zero matrix must also be of order 2 by 3 to satisfy the rules of matrix addition. In the following slides, we will look at some illustrative examples to see exactly how these square and rectangular zero matrices are constructed. Illustrative examples. Now that we have covered the definition and the key characteristics of the zero matrix, let us move on to some illustrative examples to see how this works in practice. We will begin with example 1, where we look at a square zero matrix. In this instance, our objective is to construct a zero matrix of order 2 by 2. To do this, we follow a simple 3-step process. Step 1 is to identify the required dimensions. For this specific example, the number of rows, represented by m, is 2, and the number of columns, represented by n, is also 2. Since the number of rows and columns are equal, this is why we call it a square matrix. Step 2 is the most straightforward part. Based on the definition we discussed in the previous slides, we simply fill every single position in the matrix with the value 0. Finally, in step 3, we write out the final matrix. We denote this as O sub 2 by 2, which consists of a bracket containing 2 rows and 2 columns, where every single entry is 0. This example demonstrates a square zero matrix, but keep in mind that zero matrices can also be rectangular. We will explore that in the very next example. Illustrative examples continued. Now that we have seen how to construct a square zero matrix in the previous example, let us move on to a different scenario. In example 2, we will look at a rectangular zero matrix. Specifically, we are going to construct a zero matrix of order 3 by 2. To do this, we follow a simple 3-step process. Step 1 is to identify the required dimensions. In this instance, the number of rows, represented by m, is 3, and the number of columns, represented by n, is 2. Step 2 is to apply the definition we discussed earlier. We must fill every single position in the matrix with the value 0. Finally, in step 3, we write out the final matrix. We denote this as O sub 3 by 2, which results in a matrix with 3 rows and 2 columns, where every single entry is 0. As you can see, the 0 matrix does not have to be square. It can take any rectangular shape depending on the requirements of the problem. In the next section, we will look at a real-world analogy to help you visualize how such a matrix might appear in a practical setting. Real-world analogy. Now that we have seen how to construct both square and rectangular 0 matrices in our previous examples, let us look at a real-world analogy to help you visualize how this concept applies outside of a textbook. Imagine a company that maintains a financial ledger to track expenses across various departments over several months. In this scenario, the ledger acts as a matrix, where the rows might represent different departments and the columns represent the months. If, during a particular quarter, no expenses were recorded for any department in any of those months, the resulting data table would be a 0 matrix. This is because every single cell in the table, which represents the intersection of a specific department and a specific month, would contain the value 0, indicating a total absence of expenditure. This perfectly illustrates the definition we discussed earlier, a matrix where every single entry is 0, regardless of the dimensions of the table. With this intuitive understanding in place, let us move forward and discuss some common misconceptions to ensure you do not make these mistakes in your calculations. Common mistakes to avoid. First, let's address a frequent misconception, the assumption that a 0 matrix must be square. Some students believe that only matrices where the number of rows equals the number of columns can be 0 matrices. However, as we saw in our previous examples, this is not true. In reality, a 0 matrix can be of any dimension. This includes row matrices, which consist of 1 row by n columns, or column matrices, which consist of m rows by 1 column. Secondly, be careful not to confuse the 0 matrix with a scalar matrix. To clarify, if you have a scalar matrix where the constant value, k, is equal to 0, the result is indeed a 0 matrix. But it is important to realize that not all 0 matrices are discussed or defined within the context of scalar matrices. The most important thing to remember is the defining feature. A matrix is a 0 matrix if every single element within it is 0, regardless of whether it is a diagonal matrix, a square matrix, or a rectangular one. Now that we have looked at both square and rectangular examples, let's discuss some common pitfalls to ensure you have a clear understanding before we wrap up. Keep these distinctions in mind as we move to our final slide for the key takeaways. Key takeaways. First, as we established at the beginning, a 0 matrix, which you may also hear referred to as a null matrix, is defined as a matrix where every single element is 0. To keep our notation consistent and concise, we represent this special matrix using the capital letter O. One of the most important points to remember, which we saw in our examples of both square and rectangular matrices, is that a 0 matrix is not restricted to a specific shape. It can be of any order, m by n. Finally, let's discuss its functional role. In matrix algebra, the 0 matrix acts as the additive identity. To put this simply, if you have any matrix A and you add it to a 0 matrix O of the same dimensions, the result remains the original matrix A. This is the exact same principle as adding 0 to any number in basic arithmetic, where the value of the number remains unchanged. Now, let's wrap up everything we have learned in this lesson with a few key takeaways.